Welcome to Lecture 7.2, Eigenvalues and Eigenfunctions of the Laplacian. Recall that the Laplacian is the differential operator, sometimes denoted as a triangle, other times as del squared if you're in Cartesian coordinates, which is the sum of the second spatial derivatives. In the previous lecture, we found the kernel of this operator, specifically for n equals 2, under various boundary conditions. This amounted to solving a PDE called Laplace's equation. That's the Laplacian of u equals 0. Find all functions u. And then we imposed different boundary conditions in a square region. In this lecture, we will find the eigenvalues and eigenfunctions of this operator. This amounts to solving a PDE called the Helmholtz equation. So we want to find all functions u such that the Laplacian of u is some scalar of u. This equation arises when solving the heat and wave equations in 2 dimensions, and that's what we'll do in the next lecture. We'll start with an example of finding the general solution to the following boundary value problem for the Helmholtz equation under Dirichlet boundary conditions. So the Helmholtz equation, recall, is that Laplacian of u, which is equal to uxx plus uyy equals negative lambda times u. Now, this doesn't have to be negative. We can make it positive, but we're going to make it negative just to be consistent with what we did with 1D PDEs and with regular boundary value problems and Sturm-Liouville theory. We had a negative sign out in front. So the 4 boundary conditions, the Dirichlet ones, just say that if we have this square region, say x is in this direction and y is in that direction, then if you think of u as the temperature, then that's equal to 0 along all 4 sides. Okay, we're going to solve this like we always solve it. We will assume that there's a solution that is a function of x times a function of y, plug it back in, and separate variables. So let's do that. So we will assume that there is a solution, u of x, y, which is big X of little x, and big Y times little y. And before we plug back in, we need to take derivatives. So we have, oops, it's not f, it's u. We have u x equals big X double prime times y, and u y equals big X times y double prime. And now we have our 0 boundary conditions, as I like to call it. So the first one says that u of 0y, so we're using this one right here. This is big X of 0 times big Y of y, and that's equal to 0. So we have a number here times a function equaling 0. So that tells us that the number has to be equal to 0. So x of 0 equals 0. The next condition says that u of pi y equals x of pi y of y equals 0. And as before, this is a number times a function equaling 0. That tells us that x of pi is equal to 0. And then we have 2 more. I'm not going to write them out. I mean, clearly these 2 things tell us analogous things about y instead of x. So 2 more, let's say ... And those tell us that y of 0 and y of pi are equal to 0. Okay, so let's box those. We will use these later. And now we're ready to plug back in. So let's plug our derivatives back into this PDE. So uxx plus uyy equals, well, that's the sum of these 2 things. So that's x double prime y plus xy double prime equals lambda x times y. And now what we always do is divide through, well, I've said by c squared fg, but there's no c here and we have x and y. So let's divide by xy on both sides. And so now what will happen is, so look what we have on the right-hand side, we have just lambda. Oh, I forgot let's make that negative lambda. Sorry about that. So on the right-hand side, we'll have negative lambda. On the left-hand side, we'll have x prime over x plus y prime over y equals negative lambda. So that's x prime or double prime over x plus y double prime over y equals negative lambda. We want to separate variables, so I'm going to write this as x double prime over x, let's see, plus equals, let's see, how about negative lambda minus y double prime over y. So this is, I'm going to leave a little bit of room here. This is our eigenvalue equation. So we've separated variables. Now this lambda, before we've always said, oh, okay, we put something on the left and one variable, on the right on the other variable, and set that equal to lambda. But now lambda is part of the problem. So I'm going to still do what we did before. I'm going to put all the variables, all the things of x on one side, so x prime over x. So the left-hand side of this equation does not depend on y, and it's equal to a constant minus y double prime over y. This does not depend on x. So this must be a constant, and let's set this equal to the constant. Let's call it mu. So I'm going to call this equal to mu because, again, this is independent of y, this is independent of x. Okay, so now what? Actually, I'm going to call it a negative mu. So now we have a boundary value problem in x. Okay, let's write that out. So we have x double prime equals negative mu x, and we have two boundary conditions right here. And so we have x of 0 equals x of pi equals 0. So we know how to solve that. So let's see what we have for y now. So how do we want to deal with this? So we have two constants. Let me circle this, and I'm going to rewrite this over here. So I'm going to put y on one side of the equation. Now I'm going to write y double prime over y equals, so if we do that, then what's on the left-hand side of this equation? So it's equal to negative, and what is it? Negative lambda, and then is it plus mu or minus mu? I think that is correct, right? So again, this thing circled, y double prime over y on the right-hand side. The left-hand side is negative lambda minus mu. And now this constant, lambda minus mu, I'm going to call it something else. Let's set this equal to negative nu. So in other words, I'm going to declare that nu equals lambda minus mu. In other words, lambda, that's this constant up here, lambda is equal to mu plus nu. So this is Greek for m and n. Okay, so now we have a second ODE. Y double prime over y equals negative nu. Now we didn't need to do this. It's just, we could have had two constants here. It's just easier to call it something else. So now we have y double prime equals negative nu times y, and we have y of 0 equals y of pi equals 0, these boundary conditions right here. Okay, so I keep wanting to box things because these are all important. So I'm going to box this thing in blue. We know how to solve these. So maybe I should have done this over here, but that's no problem. So we know that, let's see, what do we know? We know that mu is equal to n squared. Well, both of these are equal to n squared for some integer. So I'm going to write that as mu equals m squared. I'm going to call that mu sub m. And xm, or that should be a big X, m of x equals sine of mx. So I'm just using m instead of n, because I'll use n down here. And similarly, nu is equal to n squared. I'll call that nu n. And y n of x equals sine of nx. So this is, again, all we have here. We have two familiar boundary value problems that we've seen before. If these were L instead of pi, it would be sine of n pi x over L and sine of n pi x over L. And these would be m pi x over L quantity squared, not x, m pi over L quantity squared and n pi over L quantity squared. But now we're done. We assumed that our solution separated, and we found a solution for each. Well, actually, hold on a second. Let's see what we did. So for every integer m, we have a solution xm of x, and for every integer n, we have a solution like this. So I'm going to write it like this. So for each pair of n, or I'm going to say m and n in the natural numbers, so I mean 1, 2, 3 positive integers, there is a solution. Now what do I want to call this? Let me call this u of m n of x and y, which is this times this, which is sine of mx times sine of ny. Oh, look what I just did. I had x here and I need a y there, so sorry about that. Okay, so we have a solution, and notice that for this particular choice of m and n, lambda is equal to mu plus nu, and so lambda equals mu plus nu, which is m squared plus n squared. And so let me just write that down. Lambda is m squared plus n squared. So what that means is we have a solution to Laplace's equation, which is Laplacian of u equals negative lambda u for each lambda mn equals m squared plus n squared. Okay, so the general solution, see if I can fit this in down here. The general solution is that u of mn of x and y is the infinite sum over all m and n. So over all m and n bigger than 1 up to infinity of u m n of x, y. And then I need let's put a b m n in front of there, because any linear combination or superposition is going to be a solution. So, oops, I forgot to write m and n greater than or equal to 1. So this is one way to write this sum. We're summing over two different things, all pairs m and n that are positive integers. Another way to write that is as a double sum. You can say all sums from n equals 1 to infinity, and then from m equals 1 to infinity, times b mn, and now I'm going to put this in right here, bmn times sine of mx sine of ny. So two different ways to write a double sum. One of them you actually write two sum ins, the other one you just write one. I kind of prefer this first one just because it's simpler, but either one of these works. So let's think about what this says. So what we found is we found the general solution to the following boundary value problem for the Helmholtz equation right here. And you may be wondering, well, there's 4 boundary conditions and 4 derivatives. Why don't we have one solution? Why isn't there a unique solution? Remember, boundary value problems are more complicated than initial value problems. Recall when we first saw ODEs and boundary value problems, we saw, I was going to make right over here, but I don't need to. We saw boundary value problems like this here. 2 derivatives, 2 boundary conditions. Look, we have infinitely many solutions. And that's the case here as well. In our second example, we're going to find the general solution to a boundary value problem for the Helmholtz equation, but we're going to use Neumann boundary conditions instead of Dirichlet. So if you imagine that U represents the temperature of a square region, then in the previous example, the temperature was fixed to be 0 at all 4 edges, and now the rate of change of heat, or the flux of heat, is 0 at these 4 sides. So it's like the sides are insulated. So I'm not going to go over every detail like we did in the previous example, because that took 15 minutes, and a lot of this is just the same. So we're going to assume that u of x and y is big X of x and big Y of y. And we know that uxx equals x double prime y, uyy equals xy double prime. And now these boundary conditions are a little bit different. We'll go over them. So ux of 0 and y says that x prime of 0 times y of y equals 0. So now we have a number, x prime of 0, times a function being 0. And this tells us that x prime of 0 equals 0. Similarly, the next boundary condition tells us that x prime of pi is equal to 0. The third boundary condition, this is uy of x and 0, which is x of x times y prime of 0 equals 0. This tells us that y prime of 0 equals 0, and similarly, y prime of pi equals 0. So now we have these 4 boundary conditions. Okay, so once again, we plug back in. I think I will do most of the details before. I'm just going to do them quicker. So we plug back in, we get x double prime y plus xy double prime equals negative lambda xy. That's not a very good y, but sorry about that. So we divide by xy on both sides, xy. And then what we get is we get x double prime over x. And I'm going to move the y over to the other side, equals negative y double prime over y minus lambda. And since this depends only on x and this depends only on y, it has to be a constant. And we call that constant negative mu. So let me box that. So this gave us 2 ODEs. So we got x double prime equals negative mu times x. And we had x, these boundary conditions up here tell us that x prime of 0 and x prime of pi equals 0. And then the next one, y double prime equals, well, remember what we did here? We took this piece and we said y double prime over y equals, what was it, negative lambda minus mu, and that's equal to, we call that negative nu. So this is the same thing as saying that lambda equals mu plus nu. Okay, so y double prime equals negative nu y, and y prime of 0 equals y prime of pi equals 0. And we know how to solve these things. We know, first of all, that mu equals m squared, and x, for each m, we have a solution xm, an eigenfunction, which is xm of x, and this is equal to cosine of mx. Similarly, nu equal, that's not a nu, that's a mu. I got my Greek letters confused. Nu equals n squared, and yn of y equals cosine of my. And both of these hold for m equals possibly 0, 1, 2, 3, etc. Because if m or n is 0, then we just get a constant function, and that need not be 0. So as before, we have, so for each pair m, oh, I wrote m here, I should say n as well. So for each pair m and n that are natural numbers, and I'm going to include 0 here, we have a solution umn of x and y, which is cosine of mx times cosine of, this should be an ny, so I put an m here, I should put an n there. Okay, so in other words, we have found the eigenvalues. So lambda is mu plus nu, which is m squared plus n squared. So the eigenvalues are lambda mn, which is m squared plus n squared, and the eigenfunctions are these functions umn, which are cosines that I wrote down here. So our general solution is u of x, y. So this is the infinite sum, the doubly infinite sum. I'm just going to write it as m and n go from 0 to infinity with one sum of, let's call it amn umn of x, y. In other words, this is the doubly infinite sum from m and n, all positive integers. You don't need to write the infinity on here if you don't want to. I think it's assumed. Of amn cosine of mx cosine of ny. And that's our final solution. So of course we could pull out the constant term and call it like an a0 over 2 if we wanted to, but there's real no precedent for that. So I think it's best to leave it like this. So in summary, pretty much everything was the same except the boundary conditions. And those manifested themselves in these boundary value problems. Didn't change the eigenvalue, but it changed the eigenfunctions. We got cosines instead of sines. So let's think about what would happen if we mixed up these boundary conditions. So if two of these were Dirichlet or two of these were Neumann, one of each, that's really just going to change what we get here. And if we have mixed conditions in these and these, then we might get half integers and get sines or cosines depending on how those were mixed. So we'll do that in the next example. In our last example, we're going to find the general solution to a boundary value problem for the Helmholtz equation with mixed boundary conditions. Now that we have 4 boundary conditions, there's a lot of ways to mix them. So what we could do is, given our square region, say that this is x and this is y, we could make both of the x1s Dirichlet and the y1s Neumann, or we could make both of the 0 ones, so x equals 0 and y equals 0, we could make those Dirichlet, the other two Neumann, but I'm actually going to do sort of a mix of both of those. So in the x boundary conditions, I'm going to have them mixed, as we saw when we studied ODEs and boundary value problems, and then I'm going to make the y boundary conditions different than from one of the x's. So as before, I'm not going to go through every single detail in here, but I just want to highlight what the differences are. So we will assume that u of x and y is big X of x times big Y of y. And these conditions are going to give us the these boundary conditions are going to give us the following conditions on x and y. So this says that x of 0 equals x prime of pi equals y prime of 0 equals y prime of pi equals 0. So we're going to get the same ODE that we got before. We're going to get x double prime equals negative mu x and y double prime equals negative nu times y. But now for this first one, we're going to get x of 0 equals x prime of pi equals 0. And for the second one, we're going to get y prime of 0 equals y prime of pi equals 0. Okay, so let me actually just sketch what so at x equals 0, that's this left end point. temperature is fixed to 0 degrees, and then the other 3 endpoints, this is it's insulated. So maybe a heat equation might look something, maybe an initial condition looks something like this. I don't know how to draw that very well. It's hard. Anyways, you get the idea. Okay, so we have solved both of these before. The second one we just did in the previous example. So let me just write that down and say that nu equals n squared and yn of y equals cosine of ny. And this first one, we did this one a while ago. I think this was our example 3 in lecture 4.1. We first saw boundary value problems. And here we got, you remember that? Mu was the half integer, so m plus 1/2 squared, and xm of x was sine of m plus 1/2 x. Okay, so now we have the eigenvalues. Oh, I should say that we played this as before. Lambda is going to be mu plus nu. So in this case, it's going to be m plus 1/2 squared plus n squared. So in this case, we found the eigenvalues. The eigenvalues is for each m and n, there's an eigenvalue which is m plus 1/2 squared plus n squared. And the eigenfunctions of the Laplacian are umn of xy is sine, let's draw that a little better, sine of m plus 1/2 x cosine of ny. So our general solution is going to be u of xy. So this is going to be the infinite sum of m and n at least 0, infinity of, I don't know what to call these coefficients now. Do I call these a-n's or b-n's? Problem that we haven't had before. Let me put brackets here so we, let's just call them, I don't know, let's call them cn's. So c or cmn times sine of m plus 1/2 times x times cosine of ny. Okay, so think as an exercise, I'm sure it'll be on the homework, of what this would be if we mix these up a little bit differently. And we can even do some sort of Robin boundary conditions, which is what we saw in lecture 4.1. I could mix it up and say u of 0y plus u of what should it be? Ux of 0y equals 0. Or I could put a 2 here and a 3 here. Remember, these are our alpha i's in the general formulation of boundary value problems. Okay, so that's a good place to stop. In the next lecture, we will solve the two-dimensional heat and the wave equation. And we have all the pieces. We know how to find the steady state solution. That's Laplace's equation. In other words, the kernel of the Laplacian. And we also know how to find the eigenvalues and eigenfunctions of the Laplacian, which is what we'll need for the general solution. So we will put this all together in the next few lectures. So stay with us.